Okay, again, our goal is to come up with some sort of a closed form equation where we don't have this recurrence and don't have to explicitly go through computing to reduce the formula down to a final solution. Okay, there are three major possible strategies we could take. One of them is the substitution method. So in the substitution method, you have some sort of a guess as to what you think the solution is, and you try and prove that that guess is correct. The second approach will be using a recursion tree to do some accounting and this will work for some occurrences. And then the last approach that we'll look at in another module is the master method. So for now, we're going to focus on the first of these, the substitution method. Okay, so in the substitution method, you're going to make a guess for an exact function that satisfies the recurrence. And we'll kind of generically refer to this as f of n, not to be confused with the f of n that we've already looked at in our definition of a recurrence. So our goal is we'll pick some function. Our goal is to prove that it satisfies the recurrence after some initial start point. In order to do that, we'll use proof by induction. So we'll have to develop a base case as part of our proof by induction. Okay, so let's go ahead and look at a particular example. So we'll just look at a generically defined recurrence equation. Imagine that we've gone through looking at some algorithm and consequently developed this recurrence relation. So the recurrence relation is that the work to solve a problem of size n is the work of solving a problem of size n minus 1 plus some constant k. And we'll also make an assumption that solving a problem of size 1 is k units of work. So we're assuming that there's this existing base case. So the first step of the substitution method is trying to come up with some sort of a reasonable guess about what a closed form of the equation would look like. So if you think about this equation, let's just think about the t of 2. That would be the t of 1 plus k. And we know that the t of 1 is also k. So this simplifies down to 2k. We could think about the t of 3, and that's the t of 2 plus k, and we just solve the t of 2. So it's 2k plus k, which would be a total of 3k. Okay, hopefully you see the pattern here. T of 2 is 2k, t of 3 is 3k. So we can probably come up with a pretty good guess here. We can say that the t of n is just n times k. Okay, so we've got our guess, and we had some justification for why we think this guess is appropriate. Now we actually have to go through the formal steps of trying to prove it. So our given is our recurrence relation, and we were also given this base case. The claim is that the solution to this, the closed form solution, is just n times k. Our proof to that will start off with the base case. So t of 1 is k, so that was given. And the claim holds true there. So t of n is n times k. When n is 1, that's 1 times k, which is k. Our inductive hypothesis will be that the t of n is n times k. So again, for our inductive hypothesis, we usually assume that what we're trying to prove is true at one particular point, and we're trying to show that it induces it at the next natural number. So the goal is to show that the t of n plus 1 is equal to n plus 1 times k. Okay, so we've got our recurrence. We've got our base case. We've now got our inductive hypothesis. And we also have our goal. So in order to prove our goal, we'll go back and we'll use our recurrence relation. And we'll substitute in to our recurrence relation. So our recurrence relation was about t of n being equal to t of n minus 1 plus k. So let's think about, and we have our inductive hypothesis. We're going to assume that the t of n is n times k. So let's think about the t of n plus 1. using our recurrence relation and filling in n plus 1 in place of n. The t of n plus 1 is the t of n plus 1 minus 1 plus k. Okay, simplifying that down, obviously the plus 1 and the minus 1 are going to cancel out. So the t of n plus 1 is equal to the t of n plus k. And now we can leverage our inductive hypothesis. And we know that the t of n, due to our inductive hypothesis, is n times k. And then we're adding the k onto it. Simplifying that down, it's n plus 1 times k, which is exactly what we were trying to prove. Therefore, it's been shown. Okay, so just as kind of a quick summary here, we've shown that the t of n for this particular problem has a closed form of just n times k, and we could think of that as being in the theta of n.